In this video, we're going to take a look at rates of change, the behavior of graphs, and the difference quotient. Let me share my screen and we'll get started. We're going to start with the definition of the average rate of change. When we talk about an average rate of change, we're talking about how the y values change with respect to the x values over some specific interval. In general, what we do is we find an ordered pair at one point of the interval and an ordered pair at the other point of the interval, and we find the slope of the line that connects the 2 points. The line that connects the 2 points is called the secant line. Let's take a look at problem number 1. We want to find the average rate of change for the function 6x plus 8 over the interval where x goes from 1 to 5. These are both x values, where x is 1 and x is 5. Writing the information over here, we have the function, and this is the average rate of change over the interval from 1 to 5, where x takes on the values 1 and 5. In order to find the 2 ordered pairs, we need to evaluate the y values at the endpoints of the interval. We write our equation, opening up empty parentheses for the value to substitute, first 1 and then 5. Doing the arithmetic leads to the 2 ordered pairs, 114 and 538. To find the average rate of change, we find the slope of the secant line, which is y2 minus y1 over x2 minus x1. Now we plug in the values for our points, which gives us 38 minus 14, or 24, divided by 5 minus 1, or 4, which gives us an average rate of change of 6. This should not have been surprising because our original function was the line 6x plus 8, and the slope of the line between any 2 points on a line is the slope of the line. Now we want to take a look at the next problem. In problem number 2, we have a different function. Here we have 5x squared plus 4, which is an upward opening parabola, which basically looks like this. It's not a line, which means the rate of change will change depending on what interval we want to find it over. Again, we're looking at an interval of x values, first from x equal to itself, and then x plus h. This time, our interval consists of only variable values, but the process for finding the average rate of change is the same. What we're doing is developing skills to let us find the difference quotient towards the end of this section. The difference quotient is a way of finding the slope along a part of a curve. Why is it important? Well, the difference quotient is one of the building blocks that we use in calculus. It's a part of the definition of the derivative, and the derivative is one of the 3 major constructs in calculus. So the difference quotient is very important to the foundation of calculus, which makes it an important formula and function to learn about in algebra. What we're doing here are skill building exercises that will let us be able to evaluate that more quickly. Here we've written down the equation for our particular function, 5x squared plus 4. We're looking for the average rate of change over the interval from x to x plus h. The first one says replace the x with x. Well, we already have that. That's 5x squared plus 4. This is the ordered pair x for the x coordinate and 5x squared plus 4 for the y coordinate. Now we need to repeat the process and find the value for x plus h. When we do this for x plus h, we again write the function 5 times something squared plus 4, and then fill in the something, the empty parentheses, with x plus h. This means that we need to multiply x plus h by itself and then multiply the result by 5. When we do the FOIL process on x plus h twice, we get x squared plus 2hx plus h squared. This is then multiplied by the 5, using the distributive property to distribute across each term. The plus 4 carries on until the multiplication and division and parentheses are gone. Now we get 5x squared plus 10hx from 5 times 2hx and 5h squared from 5 times h squared plus the 4. None of these are like terms. Remember that you can cover up the numerical coefficients to see what kind of term it is. This one is h squared, this is hx, that's an x squared, and well, this is just a constant. None of those are alike, so we can't combine anything. This gives us the ordered pair x plus h, followed by the y coordinate 5x squared plus 10hx plus 5h squared plus 4. Now we want to find the average rate of change over the interval. We have two ordered pairs, x and 5x squared plus 4, and the second ordered pair that we just found here. I'm going to start with the more complicated one first, since that usually is an easier way to simplify the formula. Again, the slope of the secant line is giving us the average rate of change, which is really just the slope, y2 minus y1 over x2 minus x1. I take the y coordinate of the second one, and then I subtract the y coordinate of the first ordered pair, 5x squared plus 4. Notice that we'll need parentheses because I want to subtract both terms in the second y coordinate. This means I'll have to distribute the negative over both terms inside parentheses. In the denominator, I need the difference in the x coordinates, but in the same order as I did the y coordinates. Since I started with this y coordinate, I start with x plus h in the denominator. Then I subtract the second x coordinate, which was just x. This means that I have an x in common in the denominator, which are like terms and can be canceled. In the denominator, this gives me just h. And the numerator, the 5x squared plus 10x plus 5h squared plus 4, stays the same while I distribute the negative over 5x squared and the 4, resulting in negative 5x squared minus 4. Then I need to simplify the numerator by finding like terms and canceling them. 5x squared cancels 5x squared, and 4 cancels the negative 4. The whole thing is then divided by h. Let's rewrite the numerator in a simpler form. I have 10hx plus 5h squared left behind, all divided by h. There are two ways of solving this, and I'll show you both. One of the methods involves factoring out the common factor of h from the numerator. Why only the h, since 5 is also a common factor of 10hx plus 5h squared? The answer is I only have the single factor h in the denominator. That's all that could possibly cancel. So I factor out the h, leaving behind 10x plus 5h. Then the h's will cancel, and that leaves behind 10x plus 5h. The second method, which is actually the one I personally prefer for myself, is to split the numerator, which consists of two terms, into two fractions divided by the single term denominator. This gives me 10hx over h, and the h's cancel to give me 10x. Then the second term plus 5h squared divided by h, where the h cancels one of these two h's and gives me plus 5h. Notice that the answers are the same. You can put the answer directly in here and then check the result. If I knew what x and h were, I'd be able to get a number value for the average rate of change, which is really the slope of the secant line connecting those 2 points. Let's take a look now at number 3. Looking at number 3, we're again looking for the average rate of change, but for a function that uses t instead of x. We need to be sure that we write t when we're using our function. The function is 4t squared plus 7, which is written here. And we're looking for the average rate of change over the interval from 6 to 6 plus h. Remember, intervals are always given in terms of the x values. So x will be 6, and then x will be 6 plus h. We want to find the average rate of change, which is really just the slope of the secant line. First, we're going to take and we're going to substitute in 6 in place of the t. We write the expression for the equation, leaving empty parentheses in place of the variable t. Then we replace that with 6. The order of operations tells us to do exponents before we multiply by 4. So we get 4 times 36, then plus 7. Multiplication happens next, and 4 times 36 is 144. Plus the 7 gives us 151. This gives us the ordered pair 6, 151. Now we need to find the second ordered pair, which corresponds to the other endpoint of the interval, where we allow t to take on the value 6 plus h. We start the same way by rewriting the expression of the equation as it is seen here, but replacing the variable t with empty parentheses. Then we replace that with the expression 6 plus h. Again, we need to multiply this by itself first, and then we multiply by 4. When we multiply these two together, we get 36 plus 12h plus h squared when we apply the FOIL process or the distributive property. Then we'll multiply by 4 and add 7. It looks a little weird though, because we usually have h squared first. It's perfectly fine to go ahead and reorder it now. You can write h squared plus 12h plus 36 on the inside, but of course it's not mandatory. Then we'll need to distribute the 4 over each of the terms inside parentheses and finally add 4. This gives us 4h squared plus 48h plus 144 plus 7. The only like terms are the two constants, which we add together to get 151. This gives us the second ordered pair, 6 plus h, and 4h squared plus 48h plus 151 as the y-coordinate. Let's rewrite the first one below so we have them in the same location. That was 6, 151. Now that we have the two ordered pairs, we're prepared and ready to go ahead and find the average rate of change, which is the slope of the secant line connecting those 2 points. This is going to be y2 minus y1 over x2 minus x1. Again, I start with the more complicated y expression and I write it first. Then the formula has subtraction, and then I write the second y coordinate, which is 151. The denominator, on the other hand, will start with the x coordinate that corresponds to the one I used first, which is 6 plus h, then a minus for the formula, and then the second x coordinate, which is 6. I have two like terms in the numerator, the constant 151 minus 151, which cancel, and two like terms in the denominator, the 6 minus 6, which also cancel. Rewriting what we have, we then get 4h squared plus 48h divided by h. Again, choose your method, the one you prefer, to go ahead and reduce the problem. If you like factoring out the factor that you have in the denominator, factor it from the numerator. You're not really looking for the greatest common factor. You're looking for the factor from the numerator. And that will give you 4h plus 48. My preferred method is to take each term in the numerator and divide by the denominator. That also leads to 4h plus 48. Let's move on to the next problem. In the next problem, we're switching gears and we're going to talk about the behavior of functions. Here we're talking about where the function is increasing and where it is decreasing, and also what the local maximum and the local minimums are. First, we need to define what we mean by these terms. When we talk about decreasing, we talk about the y values that decrease over the x values given by some intervals. When we're talking about increasing, we're saying that the y values increase over the x values given by a different interval. Let's take a look here and see why these intervals make sense. How do you read the graph? You read the graph from the left side to the right side. Starting on the far left, we have negative infinity. If we put our finger on the graph and we trace the graph as we move to the right, notice that the y value is decreasing, coming down. This happens until I reach the x value of -6. 1, 2, 3, 4, 5, 6 to the left. That's where it stopped the y value decreasing. So from -infinity until x equal -6, we have that the y values are going down. These values right here represent the x values where that's happening. Then from -6 until we reach x equal -2, we see that the y values are increasing or going up in value. Over the interval from x equal -6 to x equal -2, the y values are going up. That would be the interval over which it's increasing. What happens from -2 to the far right of the graph? Again, starting at -2, we can see that the y values are decreasing again, and we can assume they continue decreasing forevermore. That means that we have another piece of the graph where it is decreasing, where the y values are decreasing. We give the x interval where that happens, starting at -2 and moving to the right to infinity. Therefore, these two intervals are where the function decreases, and this interval is where the function increases. What does it mean when it says local maximum and local minimum? A local maximum or a local minimum is the highest point for a local maximum of all the points nearby. It may not be the highest one in the entire graph. That would be an absolute maximum. Instead, it's just higher than the ones close by. Looking at the graph, we can see here that this point right there is the highest in this local area. It's not as high as these y values over here to the far left, but it is higher than the ones close to it. Where it occurs is the x value, which would be x equal -2. What the local maximum is would be the y value, which is up 1, 2, 3, 4, 5. The local maximum would be 5. What about the local minimum? Do we have one on this graph? Yes, we can see right here that we have a low value at this spot. Where it occurs, that's the x value. That is left 6 or -6. What the local minimum is, that's the y value, and that's given by -9. Remember that where the maximum or minimum occurs is the x coordinate, but what the maximum or minimum is the y coordinate. Let's move on to the next problem. In problem number 5, we essentially have a similar kind of graph, but on this graph, we can notice that we have a point that is lower than all the other points on the entire graph. This is what we mean by an absolute minimum. There is no point on this absolute value function that has a y value below this y value here. Where it occurs is at x equal -2, but the absolute minimum value is 0. Now the question here is, should it be x equal or y equal? Remember that absolute maximum and absolute minimum values are always y equal. I'll leave you to do the increasing and decreasing on your own, but again, remember to read from the left to the right. Decreasing is where the y values are going down, but you give the intervals in terms of the x coordinates. So from -infinity to -2. Increasing is where the y values are going up from left to right. But again, you give the x interval where that happens from -2 to +infinity. Let's check our result and make sure that we did that one part correctly. It's not happy I skipped the first part, but it likes my answers to the part I answered. When we're looking at this problem right here, I'll leave you to again do the increasing and decreasing, since it's similar to the one we did before. Notice that this point right here is a local maximum, not as high as these over here, so it's not absolute, but higher than the ones around. The y value is the value of the local maximum. Where it is the x coordinate. This point here is a local minimum, not as low as these y values, but lower than the y values nearby. The y value here is a negative 1, 2, 3, 4, 5. That gives the local minimum a value of negative 5 occurring at x equal 3. I'll leave you to figure out the increasing and decreasing on your own. Let's take a look at problem 7. We'll go ahead and work this one. When we're looking at this one, notice first of all that we have a point here, which is the vertex of the parabola that's lower than all the other possible points. Because it's lower than all the other possible points, this must be an absolute minimum. What's the value of the absolute minimum? That would be the y value, which is negative 1, negative 2. The y value is negative 2, and that's the absolute minimum. Where it occurs is x equal negative 1. From the left to the right, we would say that the y values decrease over the x interval from negative infinity until we reach x equal negative 1, and then increase over the interval from 1 to infinity. Problem number 8 is similar to problem number 7, so I'll leave you to work that one out. Now we want to look at problem number 9. In problem number 9, we have a table here. When you're looking at a table and you have time involved, time is usually, though not always, the independent variable. That means it takes the place of the x coordinate in the ordered pairs, going first. The other value tends to take on the dependent role and typically replaces the y coordinate in the ordered pairs. In this problem, we're to express annual sales in millions of dollars based on the year in which those sales were produced. This goes from the year 1998 to the year 2006. They want to know what the average rate of change in annual sales is between the years 2001 to 2002 and between 2001 and 2004. To find average rate of change, we need ordered pairs. To find the ordered pairs, we're going to go to 2001 and 2002 and find their related sales in millions of dollars. This means in 2001, the related sales are 243 million. And you can see we wrote that ordered pair here. In 2002, the related sales are 251 million, and you can see that we wrote that value here. Now we need to find the average rate of change by taking the difference in the y values and dividing by the difference in the x values. I decided to start with 243, which means I then subtract 251, but don't freak out. Just because it's negative doesn't mean it's wrong. Notice that because I started with 243, I have to start with 2001, and that gives me 2001 minus 2002. This gives me a negative 8 over negative 1. This basically is a rate of change of $8 million every 1 year. Now let's look at part B. In part B, we are looking at the rate of change between 2001 and 2004. We already have the ordered pair for 2001. We need the one for 2004, which is 2004, 241. I'll leave it to you to compute the average rate of change for this time interval. Now let's take a look at problem number 10. In problem number 10, we are given a basic word problem or an application problem. It says at the start of a trip, the odometer on a car reads 20,287 miles. At the end of the trip, 11 and a half hours later, the odometer reads 21,252 miles. There are two ways to set this problem up. One is through logic and the other is through ordered pairs. In the logic method, we want to find the average speed. We think about what speed represents. When we talk about speed, we're usually talking about miles per hour. When we talk about miles per hour, we need to translate this into mathematics by writing miles divided by hours. That's what per means. This would be the change in the number of miles divided by the change in the hours. We can come to a scratch area and we can compute the difference in the miles by subtracting the smaller amount from the larger amount, which gives us 425 miles. The trip lasted 11 and a half hours, and when you do the division, you end up with this decimal number here. Generally speaking, WebWork wants about 5 decimal places. That's a good place to go. Not 4, not 6, but 5. If it says use 2, then use 2. But if it doesn't say, try 5. There's another way to set this one up, which is to use ordered pairs. At the beginning of the trip, 0 hours have elapsed, so the t coordinate is 0. The odometer reads 20,827 miles. At the end of the trip, the time elapsed is 11 and a half hours, and the odometer now reads 21,252. Then you can find the average rate of change by finding the slope of the line that connects these 2 points. Let's move on to the next problem. In the next problem, number 11, we have a driver of a car who stopped at a gas station to fill up his gas tank. He looked at his watch and the time read exactly 3:40 p.m. At this time, he started pumping gas into the tank. At exactly 3:44 p.m., 4 minutes later, the tank was full and he noticed that he had pumped 11 gallons. They're asking us to find the average rate of flow for the gasoline into the gas tank. In this problem, they've helped us out by giving us the units of the average rate of flow, which is in gallons per minute. What they're talking about then is the change in the number of gallons divided by the change in time. We know that he pumped 11 gallons and it took him 4 minutes to do it. 11 over 4 represents the average rate of flow of gasoline into the gas tank. How can we represent this problem instead using ordered pairs? We have 2 choices. We could use the actual time, which is probably not the best way, representing that at 3:40 p.m., 0 gallons of gas have been pumped, and at 3:44 p.m., 11 gallons has been pumped. But this would require us to subtract the time in this notation. It would be easier to say that at the beginning of the pumping, 0 minutes have elapsed and no gallons have been entered into the tank. 4 minutes later, 11 gallons has. Then we can compute the average rate of flow by taking the slope of the line that connects these 2 points. We'll again get 11 gallons divided by 4 minutes. We're now ready to talk about the difference quotient, which I told you earlier is tremendously important in the foundation of calculus. That makes it important in algebra so that you have the skills to use the difference quotient in its definition in calculus. All we do in this class is we apply the formula and find the difference quotient value. The difference quotient is actually just the slope in disguise. Let me show you what I mean. Let's take a look at the formula right here. Remember that function notation represents the y value. So f of x plus h is the y value when x is equal to x plus h. F of x represents the y value when x is itself. This is the change in the y values, y2 minus y1. Is this the change in the x values? The first x value is x plus h, and the second x value is x. If I were to subtract these in the denominator, I would have x plus h minus x, which of course would lead to the denominator over h. In other words, what I really have is the slope, y2 minus y1 over x2 minus x1. In this particular equation, we have the formula for the function itself, 5x squared minus 10. Over the years, I've discovered that the best way for students to do this and not make a careless mistake is to do it in pieces. First, we'll compute f of x plus h. Then we'll compute f of x. Then we'll divide each of those by h after subtracting f of x from f of x plus h. When we compute f of x plus h, remember that we rewrite the formula for the function with putting empty parentheses in place of the variable, in this case, x. Then we put in the substitution expression, x plus h, in place of the empty parentheses. We need to apply the power before we can do the multiplication by 5. This gives us x plus h times x plus h, which turns out to be x squared plus 2hx plus h squared. Then we distribute the 5 over each of the terms inside the parentheses, which leads to 5x squared plus 10hx plus 5h squared, and the minus 10 follows along. None of these are like terms. That's an x squared term, that's an hx term, and that's a h squared term, while the minus 10 is a constant term. So I cannot simplify f of x plus h. The next part of the formula is to find f of x, but I was given f of x in the statement of the problem. It's 5x squared minus 10. To apply the formula, I need to subtract this expression from this expression. Because f of x has two terms, I need to use parentheses around it so that I'm subtracting both of the terms. I color-coded this here so that you could see the different pieces. F of x plus h is in blue, f of x is in this pink color, and the divided by h is in gray. Notice that I have f of x plus h as it is here with no changes. Then I have a minus for the formula that you see here. And then I wrote the formula for the function itself inside parentheses so I could subtract each term. I need to distribute the negative over each term on the inside. Then I divide the whole thing by h. Simplifying the numerator means writing it with the negative distributed. That gives me a negative 5x squared and a positive 10. If you mess up the sign, you will mess up the entire difference quotient, and things that should cancel won't. Notice that this gives us two like terms, 5x squared and minus 5x squared, that cancel, and another pair, negative 10 plus 10, that also cancel. Rewriting what's left, we can see that we now have 10hx plus 5h squared divided by h. Choose your method to simplify the fraction. Either factor out the denominator factor, which is simply h, leaving behind 10x plus 5h and canceling the h to get 10x plus 5h, or split the numerator's terms into that number of fractions, dividing each term by the denominator h, and then reducing. This next problem is rather more complicated. It's also a parabola like the last one, but notice that the variable x shows up in two places, in the negative 7x squared and in the negative 4x. This is going to make our f of x plus h much more complicated. Let's take a look. When we write this one, we're going to start again by writing the expression for the function with empty parentheses in place of the variable x. Then we substitute x plus h in place of the variable x. First, we have to square to eliminate the exponent. X plus h times x plus h is x squared plus 2x, or 2hx plus h squared. Then we'll need to distribute the negative 7 over each of the terms inside. We'll also need to distribute the negative 4 over each of these terms on the inside. Check the arithmetic here and make sure that you can follow it. Make sure you don't mess up on the sign, since that causes the biggest number of errors in this type of problem. Note that we're following the order of operation. We're doing exponents before we do multiplication and division, and addition and subtraction at the end. This is our expression for f of x plus h, and there are no common factors. Now we're going to put it into a fraction, the formula for the difference quotient, f of x plus h minus f of x, all divided by h. Here is the expression that we see from up above with no changes made to it. Then a minus for the formula, the minus here, and then we rewrite the expression for the function in parentheses afterwards. This is going to require us to distribute the negative over each of the terms on the inside, and we'll change all the signs. Then the whole thing is divided by h. First, we rewrite the part from f of x plus h with no changes. Then we distribute the negative times negative 7x squared to get positive 7x squared, the negative times negative 4x to get positive 4x, and the negative times positive 6 to get negative 6. Then we look for like terms that cancel. There should be quite a few in a problem like this. If you mess up the signs on this last part, things will not cancel that should be canceling. Be very cautious with your signs and always put f of x in parentheses. When we're done, we have left negative 14hx minus 7h squared minus 4h, all divided by h. Choose your method to reduce this and simplify. You can either factor out the factor which represents the denominator, h, leaving behind negative 14x minus 7h minus 4 and canceling the h. Or you can split the numerator, which has 3 terms, into 3 separate fractions, each one divided by the denominator h. The result is the same in both cases. The next problem that we see here is also a difference quotient, and this function is actually a line. It's written in reverse order for what we normally see for slope-intercept form. It would normally be negative x minus 5. This means it has slope of negative 1. Don't be surprised, because this is the difference quotient, if you end up with a negative 1 for the slope. Since it's a line, that's what it should be. But go through the process, as we've done here, finding f of x plus h, subtracting f of x, and dividing it all by h. This is what I'll expect to see on an exam. I'll leave you to do this one on your own. Let's take a look at the next one. This is 5 divided by x. This is going to be rather more difficult, so let's take a look at this one together. On the next problem, we write the expression for the function, which is 5 over x. Then to find f of x plus h, we write that expression, but we leave an empty set of parentheses in place of the variable x. Finally, we fill in the empty parentheses with x plus h. There's nothing we can simplify here. It's simply this fraction. Now we can write this fraction as the first part, then minus for the formula, and then we represent the second part, which is f of x. F of x is only a single term, the fraction 5 over x, so the parentheses are not necessary. You can write them if you want a rule that always works. And then the whole thing is divided by h. This makes this a complex fraction because it has a fraction inside of a fraction. To make it simpler to work, we're going to make each of the parts in the numerator and denominator into fractions. That means that we're going to rewrite the h instead as h divided by 1, which is the same thing as h. Then we look at all of the little denominators of all the little fractions we have, and we write them down. X plus h, which is a group, x by itself from this one, and 1 from the denominator of h. The lowest common denominator is the multiple of all 3, x times x plus h times 1. The 1 can be dropped, and that gives us x times x plus h. To simplify the complex fraction, rewrite it here as seen in the black notation. Then you want to multiply by a form of 1, consisting of the common denominator divided by itself, but written in complex form. So that's the lowest common denominator over 1 divided by the lowest common denominator over 1. Since there are 2 terms in the numerator separated by the subtraction, we'll distribute this lowest common denominator over both in the numerator. The denominator only consists of 1 single term, so we'll only have to multiply once. When we distribute in the numerator, notice that the group factor x plus h cancels on the first one and leaves us 5 times x, or 5x. When we distribute the common denominator over the second term in the numerator, the single x factor cancels and leaves us 5 times the group factor x plus h. In the denominator, the only thing we had in the denominator of that fraction was 1, so nothing cancels, and we get hx times the group factor x plus h, which you see here. Now we need to simplify the numerator to see if we can cancel with any of the factors in the denominator. There's no need to multiply out the denominator, it's already fully factored. But the numerator has 2 terms separated by the subtraction we see out in the open here. We need to multiply this out and simplify, and then if needed, refactor it. This gives us 5x as the first term, and then we distribute the negative 5 over the group factor x plus h, giving negative 5x minus 5h. This gives us 2 like terms, 5x minus 5x, which cancel, and gives us minus 5h as the sole remaining term in the numerator, divided by hx times the group factor x plus h. This then gives us a single factor of h by itself as a common factor between the numerator and denominator, so we can cancel out this part. We can't cancel this h because it's a part of the group factor x plus h. This leaves our final result as negative 5 over x times x plus h. Let's take a look now at the next problem, problem number 16, which is the last problem. In problem number 16, you're again going to evaluate the difference quotient, which is a formula giving a formula for the slope. When we're looking at this function, we see that we have a cubic, which means, unfortunately, when you do f of x plus h, you will have x plus h in there 3 times. Multiply 2 together, then multiply those 2 by the third x plus h, then multiply that result by the negative 4. It's a lot of work, but I know you can do it. From that point on, it should be relatively straightforward, not easy, difficult, but straightforward and like the previous examples. So I leave you to do that one on your own. I hope that you now have a better feel for what average rate of change is, how the behavior of a graph can indicate increasing, decreasing, local maximums and minimums, and absolute maximums and minimums. And finally, I hope that you understand the difference quotient, which is one of the foundation definitions for calculus.